Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series looking at developing a simple ray tracer in C++ using as far as possible only the standard libraries along with the SDL2 library to allow us to display results in a window. This episode in particular is going to focus on UV space and texture mapping, and is finally going to allow us to create some slightly more interesting scenes, and scenes with the classic checkerboard pattern floor at least, which is, some time ago was always kind of the staple of computer ray tracing images. I don't know why, but there you go. Anyway, so that's what we're going to be looking at today, which I really hope will be of interest. And just before we jump into that, I just want to say, as I always do, that if you like this video, please do remember to hit that like button. It does help a lot with the YouTube algorithm. And if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's have a look at UV space and texture mapping. Okay, so here we are, episode 9, UV space and textures. Let's just jump in. So first of all, really, what is texture mapping? Well, texture mapping is the process of taking a pattern or an image or something like that and applying it to one of the objects in our scene so that it doesn't just look as flat. You know, previously our objects have had only plain colours, and fair enough, they've had reflections and specular highlights and so on, but the colouring has really just been flat. So texture mapping allows us to do things like this, where now I've applied the typical ray tracing checkerboard pattern to more or less all of the objects in this scene. We start with, we've got the black and white checks on the floor, which is also shiny, and then we've got the checks on the sphere and the cylinder and the cone, and we have a reflective sphere here just because we can. So that's what texture mapping is. It's the process that allows us to actually do that, to put these patterns onto the shapes, and you'll see how the pattern follows the shape of the surface, but that's the important thing. So how does that actually work? Well, really the principle of this is UV unwrapping, which you can see in this animation here. So if we start with a cylindrical surface, we can actually imagine that we could essentially slice that open along one axis, along the long axis of the cylinder, and then we can actually physically unwrap it, as you can see in this animation here. And that gives us a flat surface, and we can label the axes of that surface of U and V, as you can see here, and that is then just a two-dimensional surface. Now, you can imagine we could then apply any image or pattern that we want to that surface and then simply reverse the process and to wrap it back into the cylinder in this case, and then we would have our texture or our image or our pattern or whatever mapped onto the cylinder. And that is really the basics of what we're going to do. Now, there are different ways we could approach doing this. We could try to calculate exactly what kind of mathematical transforms would be required to map a two-dimensional image onto the particular object that we have, but that would be really very complicated. We're not going to try and do it that way. Instead, because we're building this into our ray tracer, we're going to use the fact that we know the point of intersection with the object. And if you remember to the previous episodes, we're defining our objects in their own local coordinate systems. So that's actually really quite straightforward. And then what we're going to look at instead is how we map from that point of intersection to an equivalent two-dimensional UV point on the surface of the object. And actually any object can be unwrapped in some way, not necessarily continuously. As we will see a little bit later on, there's a little bit of complexity with, for example, the end caps on cylinders, but we'll come to that. Okay, so that's really the basics of what we're doing. Let's have a look at what that really means. So what we end up with is a UV space defined like this in two dimensions, which we've labelled U and V, hence that's why it's called UV unwrapping, or UV space. And we're going to arrange our UV space so that it goes from -1 to 1. In both axes. And what we're going to do is write code for each object in our ray tracer that maps any point of intersection onto some point in this UV space between -1 and 1 in both U and V. Okay, so let's consider planes first, because they're kind of the easiest case. So if you remember back to the episode where we talked about planes, we have the standard vector equation for a plane is given here. The vector x is p0 plus p01u plus p02v. And it's not a coincidence that these are u and v. So these are scalar quantities that represent some distance along these two vectors. We have an origin vector, and then x is simply the vector of all of the points on the plane. And then to actually implement the plane in ray tracing, we took the equation for a line, which is simply that. L is equal to a plus tk, as we've seen before, and then the point of intersection we get if we make those two equations equal to each other, and then we can rearrange that into vector notation like so, and so we get a system of three equations, three unknowns, which are t, u, and v. So this is just a slide from the previous video about how we're defining things in our local coordinate system, which makes things very simple. We've talked about that before. We don't need to go over it in great detail now. But what that means is we can rewrite the equation for our point of intersection as simply this. The vector a is equal to scalar u multiplied by the vector 1, 0, 0, plus the scalar v times the vector 0, 1, 0, minus the scalar t multiplied by the vector k. Or, in other words, that the x component of a is equal to u minus kxt, and the y component of a is equal to v minus kyt, and the z component of a is equal to minus kz times t. And of course that's exactly what we use to get the value for t. And then to find the point of intersection, we substitute the value of t back into those equations, which is pretty straightforward. But what it also means, as well as calculating the value of t, we can actually extract values of u and v directly simply by rearranging those equations. So we get that u is equal to ax plus kxt, and v is equal to ay plus kyt, and that's it. That's u and v. And u and v therefore represent our point of intersection as a two-dimensional as a point in a two-dimensional space on the surface of our plane. So if we imagine an arbitrary plane like this arranged in the three-dimensional xyz space, the plane itself has two axes, which I've labelled u and v. As you can see, there's any point on that plane can be represented both in the three-dimensional xyz coordinate system, but also as a single point in the two-dimensional uv coordinate system, which is then the value that or the coordinate that we would then use to do our texture mapping. So that's pretty straightforward. It gets a bit more interesting as we start to look at other types of objects. So for a sphere, here we have a sphere, a unit sphere defined in our xyz coordinate system, and we have some point of intersection here shown in turquoise. And if we just annotate that with various things, so we have a vector from the origin to our point of intersection here, and then I've just labelled the two axes of the sphere with the orange and the yellow circles respectively. And of course, any point on the sphere can be expressed in spherical coordinates. So a value of u, which is the angle around the orange circle, and a value of v, which is the angle around the yellow circle, and a value of r, which is of course the radius or the distance from the origin. So any point on the surface of the sphere we can represent like so. Okay, the radius of course is fixed to 1 in our case because we're only dealing with unit spheres centered at the origin. So given that we already know the xyz location of the point of intersection, that means that all we need to do is to convert those into spherical coordinates, and we can do that using the completely standard way of converting between Cartesian and spherical coordinates, so that we get u is equal to the arctangent, or tan to the minus 1, of x squared plus y squared divided by z, and v is equal to tan to the minus 1, or the arctangent, of y over x. And then we simply normalise those to be between minus 1 and 1. Depending exactly how we implement this, these will probably vary between minus pi and pi, so normalization, we simply divide by pi. And that's it for a sphere. Really quite straightforward. Okay, so a cylinder starts to get a little bit more interesting, but actually is fairly similar. So we have a cylinder here defined, shown in yellow, defined on our xyz Cartesian coordinate system. And as before, we have a point of intersection, represented by the turquoise spot here. And then we can define any point on the surface of our cylinder in cylindrical coordinates by an angle theta, okay, the radius r, of course, and z, which is the vertical point, so the point that we are up and down in the z-axis. So again, as for the sphere, we already know the xyz location of the point of intersection, which means we can convert into cylindrical coordinates very simply, that u is simply equal to the arctangent of y over x, v is simply equal to z. Okay, so we get u is our angle around the cylinder, and v is then simply our height up and down the cylinder. And I put a note here to say that in practice we use the a cos 2 function to compute tan to the minus 1, because that will automatically handle the various edge cases. Most programming languages, including C++ and the standard libraries, implement some function of, oh, I wrote a cos 2, it's, my apologies, a tan 2, obviously, for the arctangent. I don't know why I got that wrong. to compute tan to the -1, not a cos 2, a tan 2, right? But most programming languages, particularly C++, will implement some kind of a tan 2 function as opposed to simply a tan for the arctangent that deals with all the various edge cases. For example, when x is 0, okay, then this wouldn't make any sense if you just used the normal one and that kind of thing. Anyway, we don't really need to worry about that. Okay, so moving on. The end caps I mentioned are a little bit different. Now, there's various ways we could approach dealing with the end caps. We could consider the geometry of slicing them and unwrapping them to match the cylinder. That would be really the proper way of doing it. Now, I haven't done it that way because it just felt a little bit over the top, really, for what I want to do. So what I've done, I mean, the end caps are defined as planes, okay, but then we ignore any points that are more than 1 unit away from the origin, which of course gives us the unit disk shape that then fits onto the end of the cylinder. And we've already seen that computing UV for a plane is really very easy. And as the end caps are unit disks, the task is actually even easier. Remember, we define objects in their own local coordinate system, so the end cap will always be a disk with radius 1 centered at the origin, but it will have in x and y, but it will have a value in z. And simply means that UV is equal to xy. It really actually is that simple. This does work, but what it does mean, of course, is that essentially we're unwrapping the end caps separately to the actual surface of the cylinder itself, and it does mean, of course, that the texture doesn't flow smoothly from the surface of the cylinder onto the surface of the end cap, which is, you know, a little bit of a design flaw. But like I say, really for what I'm trying to do and everything, I felt that this was good enough. We may later on come to look at tidying that up, or more likely what I will do is rewrite the code at some point in the future so that we can apply a separate texture or colour to the end caps compared to the surface of the cylinder itself. Anyway, we'll see about that later. Cones we treat exactly the same way that we handle as a cylinder. So we have this geometry here, we have a cone. This is the geometry that we specifically implemented, so that the apex of the cone is at the origin in the Cartesian space. And again, we have our point of intersection with a turquoise dot, and so any point on the cone we can represent using theta, r, and z as before, so just convert to cylindrical coordinates. So as before, we get the u is equal tan to the arctangent of y over x. V, though, now is equal to 2z plus 1. Now, if you have to think about that, because the cone is defined between -1 and 0, and we want v to vary between -1 and 1. Okay, so what we do is we multiply that by 2, which then gives between 0 and -2, and we simply add 1. So we then get values between -1 and 1. Okay, so that's it really for the theory. What we're going to do now is jump into how we modify the code to actually make this work. So there's a little bit of new code to create the classes to handle the textures, and we're going to put those into a new subdirectory. And also, there's a little bit of modification to some of the code that we've created, but notably the object classes. The implementation of the object classes so that they can return the UV coordinates at the point of intersection if we want those, and a few other bits and bobs, but you'll see that as we go along. So let's jump into it now. Okay, so just quickly at my terminal, I've gone ahead and put the code into a directory here. I've called it episode 9 code. If you're following along, then you just carry on in whatever directory you're working in, or if you've got the code from GitHub, link to that in the description below, by the way, then carry on working in whatever directory you cloned the repository into. So just to quickly illustrate, if we go into the QB Raytrace subfolder, we'll see that I have created in here a new directory called QB Textures, and if we go into that, I've already created the empty files for texture base, which would be our base class for the textures, flat, which is for a completely flat texture with no pattern, and checker, which is the basic checker pattern. So that's all we've implemented so far. At the moment, those files are empty, but we're going to come to populate those momentarily. Everything else is as it was, I believe. Yes. Okay, so ready to go. So there we go. Now, the first file that we're going to have a look at then is how we go about actually creating the code to implement the base class for our textures, which we're going to call texturebase.hpp. So let's have a look at that now. Okay, so here we are. This is texturebase.hpp. I've created this simply as a blank file in the QB textures subdirectory, as we've just seen. So the first thing we're going to do is our include guards, as always, hash if ndef texturebase _h. And if we haven't defined that, then we define it texturebase h like so, and hash ndif. Okay, you always do that. And we're going to bring in a few things. We're going to hash include memory so that we can use shared pointers. We're going to hash include / qb linalg. From the linear algebra library, you need qb matrix.h, like so. And we're going to bring in qb linalg / qb vector.h. Okay, we need those, and we need finally just one last thing, / ray.hpp. Okay, now we're going to put everything into our qbrt namespace as we have been doing, which allows us just to keep everything tidy. Now, one thing I'm going to do that's a bit different here, I'm going to create a new namespace here called texture, which will help to keep things tidy. So we have a namespace within a namespace. So we access that as qbrt : texture : whatever. Okay, you'll see that in practice a bit later on. It helps to keep things tidy. We can create a class texture base like so. Okay, and we have our public functions. So first of all, of course, the constructor destructor pair. If I could spell constructor destructure, that's wrong, isn't it? Destructor. Okay, there we are. Right, I do like to spell things right, even if I'm not very good at it. So we have our constructors texture base, and then we have virtual tilde texture base, like so. Okay, and semicolon. Bearing in mind, of course, this is the base class. It's designed to be inherited by other things. So now we have a function to return the color at a given point in the UV coordinate system, right? So that's going to be the core function, really. We declare that as virtual qb vector type double. It's the return type, get color, and it accepts as input const qb vector type double reference UV chords. Okay, just that. That's pretty straightforward. One thing to note, we are going to note that the color is returned as a 4-dimensional vector. Okay, so we have RGBA. Okay, so we are allowing for alpha. We're not actually going to use that for anything at the moment, but moving on in the future we will. Now, an interesting thing I bothered to implement here is we're going to allow geometric transforms of the texture. So we have a function to set the transform. Okay, so we have void set transform. This simply allows us to scale. Really, that's the important thing, to allow us to scale our texture to whatever size that we want it to be. So this accepts as input const qb vector double reference for translation, so we can translate it. Const double reference rotation. It's 2-dimensional, remember, so we only have one angle for rotation like that. And finally, const qb vector double reference scale. Okay, and semicolon. And we've created the prototype for a function to blend RGBA colors, but returning a 3-dimensional, if I could spell 3-dimensional RGB result. Okay, but we're not actually going to use that for anything just at the moment. Again, just thinking ahead a little bit. Blend colors. At the moment, that accepts const std vector qb vector double, so a vector of qb vectors of type double, like so, reference input color list. Right? Okay. That is also should be declared static so that we can reference it without reference to a particular class. And finally, we have our function to apply the local transform to the given input vector. Okay, so we have qb vector double for our return type, qb vector double, apply transform, like so, const qb vector double reference input vector, like so. Okay, right, and that's it for our functions. We don't have any private functions, but we do have some private members. We need to initialize the transform the identity matrix. Okay, so we have QB matrix 2 of type double. Going a bit slow, make sure I get this right. M underscore transform matrix, and we initialize that to 3 by 3, and then std vector double, and this will be the 3 by 3 identity matrix. So 1.0, 0.0, 0.0, 0.0, 0.0, 1.0, 0.0, 0.0, 0.0, 1.0. Okay, and semicolon. There we go. And save that. That is everything that we need. So if you remember back to the episode where we looked at geometric transforms, we defined 4 by 4 transform matrices when we were dealing with 3-dimensional vectors. So in this case, we're dealing with 2-dimensional vectors. So we have a 3 by 3 transform matrix for exactly the same reasons. Okay, there's a link to that video in the description below if you want to go and check that out and cover that in much more detail. Okay, so let's have a look at texturebase.cpp. Okay, here we go. I've simply created the texturebase.cpp file in the QB textures subfolder. So first of all, we hash include obviously texturebase.hpp that we've just defined, and we're also going to bring in here cmath. So hash include cmath like so. Okay, so we have constructor and destructors first. So qbrt : texture : texture base. So we have to do that because we have our qbrt namespace and then our texture namespace, and then of course the class itself. Texture base : texture base. This is the constructor, doesn't do anything. And qbrt : texture : texture base : tilde texture base. That is our destructor, also doesn't do anything. Function to return the color at a given UV location. Okay, so QB vector double qbrt : texture : texture base : get color const QB vector double reference UV chords. Right, just like that. Now this is going to be specific to, you know, whatever texture we have. So really, in the base class, all we need to do is to set up the output vector, which is QB vector double output color, and it's 4-dimensional. Okay, and return the output. Okay, so return output color, just like that. Okay, pretty straightforward. Now, function to set the transform matrix. This has a little bit more code to it. So this is void, there's no return type. Void qbrt : texture : texture base : set transform const qb vector double reference translation const double reference rotation and const qb vector double reference scale. Okay. So here, what we're going to do first is build the transform matrix. Okay, from the individual components. It's pretty straightforward. So QB matrix 2 type double rotation matrix is equal to 3 by 3, right? 3 by 3 by std vector double, like so, open. And I'm just tabbing these out because I like to do that. I just think it helps keep things tidy. So here we have cosine rotation, comma, minus sine rotation, comma, 0, comma, and then sine rotation, comma, cosine rotation, okay, 0, and then comma 0.0, 0.0, 1.0, and that is our rotation matrix, okay, just like that, right? So that is the standard form of a 2-dimensional rotation implemented in matrix form, and of course we've done it using homogeneous coordinates, so it's 3 by 3. As I say, you know, you can go back and watch the previous video on geometric transforms. There's more information about that there. So QB matrix 2 double scale matrix, right? So exactly the same, 3 by 3 by std vector double open curly bracket and tab into it. Let's just keep our tabs nice and tidy. Okay, so this is our scale matrix. So scale.get element, scale is a vector, so scale.get element 0, 0.0, 0.0, and 0.0, scale.get element 1, 0.0, 0.0, 1.0, just like that. Okay, and finally we have QB matrix 2 double translation matrix, right, which is equal to 3 by 3 std. This is exactly the same, std vector double, open that and tab to here. So to define our translation matrix is 1.0, 0.0, translation dot get element 0, comma 0.0, 1.0, translation dot get element 1, comma 0.0, 1.0, just like that. Okay, and then finally the last bit of code that we need here, and combine to form the final transform matrix. Okay, so M transform matrix is equal to translation matrix multiplied by rotation matrix multiplied by scale matrix, just like that. Okay, and that is it for that function. Now I'm just going to put some blank lines in so that we can type in the middle of the screen. Okay, so the function to blend colors doesn't do anything at the moment. Blend colors, but we define it anyway. So that was a return type of QB vector double. It's QBRT : texture : texture base : blend colors. Accepts as input const std vector of type QB vector of type double. Reference input color reference, not pointer. Reference input color list. Okay. And all you have to do in here is to set up the output color, which is QB vector double output color at 3-dimensional, and return the output. Return output color, just like so. Okay. And finally, function to apply the transform. Okay, so we go to the effort to define our transform matrix, might as well do something with it, right? So QB vector double QBRT : texture : texture base : apply transform, right? Accept as input const QB vector double reference input vector. Okay, so it's going to apply the transform to the input vector and return the result. So first of all, we copy the input vector and modify to have 3 elements. Okay, because it's in UV space, so it will be 2-dimensional. So we have QB vector double new input 3, right? And then simply new input dot set element 0 to input vector dot get element 0. And of course you could put that into a loop, but I didn't really see the point just for 2 lines. There we go, input vector get element 1. Okay, just like so, right? Then we're going to apply the transform, right? So QB vector double result is equal to M underscore transform matrix multiplied by new input, just that, and produce the output. Now the output has to be 2-dimensional, okay, so we have QB vector double output 2, right, 2-dimensional, output dot set element 0 to result dot get element 0, like so, and output dot set element 1 to result dot get element 1, just that, and we ignore the 3rd element and return output, and that is it. So that is everything that we need: texturebase.hpp and texturebase.cpp. Okay, so let's just save that. Right, now the next thing we need to look at, we need to modify our make file a little bit just so that it picks up the files that we're putting into our new QB textures subdirectory. So let's look at that now. Okay, so this is the make file that we have now. All we need to do is add one extra line here. So after this line where we deal with QB materials, we just add one more slash like that, and then we basically the same $pat s sub st %.cpp, %.o, dollar open bracket wildcard dot slash QB ray trace slash QB textures slash star.cpp, and close the two brackets and save. That is everything that we need to modify there. Okay, so in theory, now if we go ahead and compile our code, hopefully we won't get any errors. Let's give that a go. Right, so back at my terminal window, if I run make now, it should pick up and compile the new texture base class. It has to compile everything because I'd run make clean, so QB primitives, QB lights, QB materials, QB textures. There we go. So we've picked up a texture base flat and a checker. Of course, they don't have anything in, but we've compiled without any errors. Now, obviously, if we were to run our code now, there wouldn't be any change. We need to actually make some changes to our code now to implement texture. So the first thing that we're going to do is look at the object base class that we created. So this is in the QB primitives directory, object-base.hpp. Let's look at that now. So here we go. This is object-base.hpp, and we just need to add a little bit down here, just down at the end. So here we have this flag bool m has material is equal to false. And what we're going to do is add a couple of lines here to store the UV coordinates from a detected intersection. Okay, if we store them, it allows us to retrieve them at some point later. And so we have QB vector double m underscore UV chord 2 semicolon. Okay, and that's it. That's everything that we need there. So that's a really very straightforward change. All we're doing is putting into the base class a member variable called m underscore UV chords. It's two-dimensional, that allows us to store the UV coordinates of any position, and that's declared public, so we can access that then from anywhere. Okay, so now we need to look at our specific object implementations. We're going to start with object_plane.cpp, so let's look at that. So here we go. This is object_plane.cpp, and what we need to do here now is to actually write the code to calculate the UV coordinates and store them in the member variable that we've just created. So let's have a look. So down here, so line 84, where we have local color equals m underscore base color, what we're going to do is just add extra code here to store the UV coordinates for possible later use. Okay, now we don't need to calculate them because we've already done it. If you remember, we actually calculated U and V up here, and then we use them because we're defining finite planes. So all we actually have to do is store them in the case of the plane. So that's super easy. So m underscore UV chords dot set element 0 to U, right, and m underscore UV chords dot set element 1 to V, and that's it. Okay, so that's everything we need to do for planes, object plane. So the next one, let's have a look at object sphere.cpp. Now for that one, we'll have to do a little bit of calculation as we saw in the slides just now. So let's look at that. Okay, so object sphere.cpp. Now here we have to do a little bit of calculation because we're not getting U and V out naturally from anything that we're doing. What we're going to do is come down to this code here, line 99, where we have local color equals m underscore base color. We are going to compute, if I could spell, compute and store UV coordinates for possible later use. Okay, so right, now we looked at how we can do this. First thing we need to extract is our variables x, y, and z representing the point of intersection in Cartesian coordinates. So use double x is equal to POI dot get element 0. Okay, remember POI we've calculated here. This is the point of intersection before we apply any transforms to it. Okay, so y is POI dot get element 1 and double z POI dot POI not pot POI dot get element 2, like so, right? And now we calculate U and V from those. So double U, now we saw this before, we use a tan, right, like so, SQRTF, floating point square root, power x, comma 2.0, so that's x squared, plus pow y, comma 2.0 is x squared plus y squared, divided by z, and close the semicolon, and then double v is equal to a tan y over x, just like that, okay? And then we've got if x is less than 0, then we do v plus equals m underscore pi, okay? And then just to normalize u, divide by equals m pi like so, and v divide by equals m pi like so. And then we simply store them. So m uv chords, that's the member variable we just defined, dot set element 0 to u, and m uv chords dot set element 1 to v, semicolon. And that's it. That's actually how we implement what we saw in the slides. It may have looked a little bit complicated, but you see, really, the implementation is really very, very simple indeed. Okay, so let's move on to cylinders. Now, cylinders are kind of similar to spheres for the cylindrical surface, but get a little bit more complicated for the end cap. So let's have a look. Okay, so here we are, cylinder.cpp. So first of all, we are going to look at, there's quite a lot of code there for the logic, and where do we come to? 161, so this block here. So line 182, we have where we return the base color, so local color equals m underscore base color. So this is, we're inside the code here that computes the intersections with the cylinder itself. Okay, so as before, we're going to compute the UV coordinates and store for possible later use, right? So we're going to do exactly the same thing. Double x is equal to valid POI, we called it in this case, dot get element 0, y, valid POI, get element 1, and double z. You can probably guess where this is going to go. Valid POI dot get element 2, just like that. Okay, so now we compute u and v. Double u equals a tan 2 y comma x divided by m pi to normalize it, and double v equals z. Yeah, just that. And then we store that. So m underscore uv chords dot set element 0 to u, and m underscore uv chords dot set element 1 to v. Okay, and just save that. So that's everything we need for that. But we need to do the end caps as well. So we need to drop down to line to here. So this is a bit of code that deals with the end caps. Again, we have local color equals m underscore base color, and just there we are going to compute and store UV coordinates for possible later use. Okay, so really much the same. Double x equals valid POI dot get element 0, double y equals valid POI dot get element 1. Now we don't need z, but I've put the code in to extract it because I'm thinking at some point in the future I might come back to this code and tidy it up to work a little bit better. So what we need to do here is m underscore uv chords dot set element 0 to x, and m uv chords dot set element 1 to y, and save, and that's it. So that is cylindrical surfaces and their end caps. So finally, let's look at cones. Okay, so cone.cpp, this is pretty much the same really as cylinder. So we come down to line, where are we? 145, so here, yes, so line 167 where we have local color equals m base color. We do pretty much the same thing. We are going to compute and store the UV coordinates. I'm not going to write for possible later use again. I think that message has got through now. A valid POI get element 0, double y, valid POI dot get element 1, z, valid POI dot get element 2. Okay, and double u is a tan 2 y comma x divided by m pi, so that's exactly the same as for the cylinder, but v is different. Double v is equal to z multiplied by 2.0 plus 1.0, okay? And then we store those m underscore uv chords dot set element 0 to u, and muv chords dot set element 1 to b, and save. So that's that. And then we just need to deal with the end cap, of course. So line 199 here, where we have local color equals m base color, we need to put in our new code here, compute and store the UV coordinates, okay? So we have double x is equal to valid POI get element 0, double y is valid POI dot get element 1, and double z valid valid POI dot get element 2. Okay, so that's pretty straightforward, and then we just store those, right? So underscore UV chords dot set element 0 0 to x, right, and underscore UV chords dot set element 1 to y. Okay, and save. Again, I bothered to extract z because I'm thinking at some point in the future I might come back to that. Okay, so that is everything really for there. Now, what I want to do, we've modified all of the object classes, so I'm going to drop back to the terminal window and let's just compile and make sure we can do that without any errors. Okay, so here we are. Let's just run make. That should go through, recompile all of those. Okay, we do have an error, set element. Obviously that's wrong. In cylinder.cpp line 221, let's have a look. Line 200, yes, there we go. That is an M, so save that. Let's just check that again. And okay, that all compiles without difficulty. Now, of course, at the moment, we can't do anything without textures. I want it to write the code in such a way that we can assign a texture to a specific material. So that's what I want to do now. We're going to look at the material base class. I'm going to add some code to actually allow the texture to be assigned to the material. And the point of doing this is the material already does the calculations for the color, and it's going to do that now with using a texture if one has been assigned. Okay, so let's look at that. Okay, so we're going to start in material base.hpp, the header file for the material base class. So the first thing we need to add an include file. Okay, so we need to hash include /qb textures /texturebase.hpp. Of course, we need to bring that in. And then we need a function to actually allow us to assign a texture, which we're going to put in after, yeah, down here at the end. Right, so this is going to be, here we go, function to assign a texture, right? Function to assign a texture, void, doesn't return anything, assign texture, and it's going to accept as input a const to std : shared ptr of type qbrt : texture : texture base, like that, reference input texture, okay, close brackets, semicolon. Right, and that's everything we need there. And then in public we have our counters for the rays, and now we're going to store down here, we're also going to have a list of textures assigned to this material, right? Let's just move that up a bit. So we have std vector of type std shared ptr of type qbrt texture : texture base, right? m_texture list. So that will allow us to store a list of textures for this material. And my thinking is I ultimately want one material to be able to hold multiple textures, and that's why we're bothering to define 4-dimensional colors for our textures in RGBA, so that we can obviously have an alpha. We also need a flag to indicate whether at least one texture has been assigned. Okay, so this is a bool m_has as texture, and we'll initialize that to false. Okay. Right, so that is everything for material-base.hpp, and that's the first point at which we're actually going to hash include our new code. So I think we should have a look at that. First of all, of course, material-base.cpp, right? Let's have a look. So in material-base.cpp, we need to implement our function. We come down to here, so return intersection found. So right just at the end here, we're going to have our new function to assign a texture, right? So void qbrt : material base : assign texture, const std : shared ptr qbrt : texture : texture base, like so, reference input texture. Okay, just like that. And what we're going to do in here is m_texture list dot pushback input texture. Just that, right? Easy. And m_has texture equals true, semicolon. Okay, that is everything that we need. So what we should do now, let's just compile and check that that works. Back to my terminal window, re1 make, recompiles material base, everything works. We don't have any errors. Okay, so now we need to just modify our actual material class instances so that they can make use of the texture if one has been assigned. So let's start by looking at simplematerial.cpp, which is of course in the QB materials subdirectory. Okay, so simplematerial.cpp. Now let's have a look. So we have down here, we have compute the diffuse component here on line 50, and what we're going to do, we have a new line here, if not m_has texture. So if this material has no texture defined, then we calculate diff color for the diffuse color exactly the way we did before. Right? Else, we now have diff color is equal to compute diffuse color. So we use that same function, and we still pass through it the same thing. So object list, light list, current object, that's all fine, int point, local normal. And now instead of passing m_base color, we are now going to pass m_texture list at 0, right? So at the moment we're only supporting a single texture, right? We've got scope for future expansion there. And we want to access the get color, and we want to pass to that current object UV chords. Okay, so that's the really powerful thing. What we're doing instead now is we've modified that code. So if a texture has been assigned, when we call the compute diffuse color function, instead of passing simply the base color, we interrogate the relevant element of our texture list. In this case, we're only dealing with the first one. Okay, that's hard coded for now. And we call its getColor method, and we pass the UV chords that we extract from the current object. And of course, those were assigned when we tested for this intersection. Okay, so see how that works. I think that's pretty good. Okay, that is everything we need to change there in simple material. And that's it. Right, so let's just check everything still compiles. Back to my terminal window, run make. Okay, run make clean because I just want to force it to compile everything. Okay, that's good. Everything compiles without error, but of course we haven't actually implemented any textures yet or used them in any way. So that's going to be the next thing that we're going to do. We are going to create some new classes to handle textures. Right, so the first one I've simply called flat. So this is flat.hpp, which I've created in the QB textures directory. So hash if ndef flat h hash define flat h hash ndif. Okay. Now this is going to be the most basic form of texture. It's just simply a flat color. So I'm thinking ahead a little bit in terms of where I want to go with this in the future. So this might not seem like it has any purpose at the moment, but I think that will become clear. So this exists in the nested namespace texture. It's class flat. It inherits from texture base, and oh, see, I've forgotten. We have to hash include texturebase.hpp there at the top, of course. So class flat inherits from public texture base, like so. Okay, and it has its own public. It has its own public things. We have the constructor destructor pair as always. So we have flat and virtual tilde flat override as the destructor. And then function to return the color. Okay, so we have virtual QB vector double, like so, get color, and accept this input const QB vector double reference UV chords override. Okay, function to set the color. Okay, so if you define a texture, obviously you want to configure it. So we need void set color const QB vector double reference input color. Now notice we didn't define this in the base class for textures, and that's because of different textures are going to have different kinds of color parameters. Some might have just one color, some may have two colors, some may have more, you know, or all sorts of other parameters. Okay, so, and we just need, spell that wrong, private So we need one private member variable, qb vector double m underscore color, and it's 4-dimensional. So all our colors for textures we are defining as 4-dimensional. Okay, so we can have RGBA. Let's save that. Okay, that is flat.hpp. So let's look at flat.cpp. Okay, so flat.cpp, obviously we're going to hash include flat.hpp. Okay, and then we have our constructor destructor, just like this. So qbrt colon texture colon flat colon flat. Generally, it's never good practice to use more than 2 levels of nesting with namespaces, because it simply gets too cumbersome anyway. So in our constructor, we're going to set up qb mcolor to qb vector double std vector double, and we're going to set it to 1.0, 0.0, 0.0, 1.0. So if we don't define a color, the default value is red. Okay, and then qbrt colon texture colon flat colon tilde flat for the destructor, which doesn't need to do anything, and function to return the color, right? So this is qb vector double qbrt colon texture colon flat colon get color, and const qb vector double reference uv chords. And this doesn't actually have to do anything at all, return m color, right, because it's a flat texture, so there's no variation anyway. And of course we need function to set the color. Okay, so void qbrt colon texture colon flat colon set color, const qb vector double reference input reference, not pointer, reference input color, like so, and simply store it, right? M color equals input color. Okay, and let's save that. Now that's really basic, but it just really shows how the texture class works. So what we have is this function to return the color that accepts as input any pair of UV coordinates, and then it will do some calculation if necessary and simply return the color corresponding to that calculation. Now, of course, for a flat texture, which is just a plain color, no calculations are necessary. Okay. So, just to make things a bit more interesting, we're going to define a checker texture as well, okay? So, let's have a look at that. So, first of all, of course, we need checker.hpp, so which I've defined here. So, we have hash if n def checker h hash define checker h hash n diff, right? And so we need to hash include texturebase.hpp. And then we have namespace qbrt namespace texture, and then class checker colon public texture base, like that. And we have our constructor and our destructor, like so. Checker as a constructor, virtual tilde checker for our destructor override, like that. Function to return the color, it's exactly the same, which is virtual qb vector double get color, const qb vector double reference uv chords, like so, override. We need function set colors. Now, of course, this is where it gets a little bit different, right? So this, we call it set color the same, but this, of course, needs 2 colors for a checkerboard, right? So we have qb vector double reference input color 1 and const qb vector double reference input color 2, right? Just like that. Okay, and then we have our private members. Like so. Our private members, we have, of course, qb vector double m underscore color 1 4 and qb vector double m underscore color 2 4. Okay, that is checker.hpp. So let's look at the cpp file. right? Checker.cpp. So of course, hash include checker.hpp, of course. We have our constructor and destructor pair, as before, qbrt, colon, texture, right, colon, checker, checker. This is the constructor. All we're going to do inside here is define default values for mcolor1 and mcolor2. So qb vector double initialize with std vector double. Going to have this as white 1 1 1 1 1. So for white 2m color 2 is qb vector double std vector double, and we're going to have this dark gray 0.2 0.2 0.2 1. Okay. And then we have our destructor, qbrt, colon, texture, colon, checker, colon, tilde, checker, destructor, which is blank, we don't need anything there, and function to return the color. So this is where we're actually going to implement the checkerboard pattern, right? So it's qb vector double, qbrt, colon, texture, colon, checker, colon, get color, const qb vector double, reference UV chords. Okay, so now let's have a look. So first of all, we apply the local transform to the UV coordinates. Okay, so we have qb vector double input lock is equal to UV chords. We make a copy of that, and then we have qb vector double new location is equal to apply transform input location, right? And then double new u is equal to new lock dot get element 0, and double new v is new lock dot get element 1. Okay, so that allows us to specify scaling or translation or rotation, which are then applied to the texture, and it achieves that by modifying the UV coordinates that have been passed. Okay, so now we're going to define our color. So we have qb vector double local color, okay, which is four-dimensional, right? And we're going to define a variable called an integer variable called check. So int check is equal to static cast, right, int and floor new u, okay, plus static cast to int of floor new v, close bracket, close bracket. So, okay, so we're static casting to int the rounded down values of new u and new v. So we'll see in a moment why we do that. So we have if check modulo 2, so check is an integer variable, so if check modulo 2 is equal to 0, like that, right, then local color is equal to m color 1, right, okay, else local color equals m color 2, semicolon. That's it. That implements a checkerboard pattern. It's really that easy. Return local color, semicolon, and that's it. And then finally, we need our function to set the colors. So it's void qbrt texture set color const qb vector double reference input color 1, and the const qb vector double reference input color 2, and that's simply going to store those lines. So it's dead easy. M color 1 equals input color 1, and M color 2 equals input color 2, semicolon. Okay, that is everything that we need then to implement those basic functions. So let's just save that. Now, so what we're going to do, let's just compile and run that, make sure that everything still works. Back to our terminal, let's run make. Okay, no, it didn't, so we've got some problems. Checker.cpp line 42 should have been declared inside. Okay, let's have a look at that. So checker.cpp line 42. Checker.cpp line 42. I've probably done something really obvious. Yeah, qbrt texture checker set color. So let's save that. Let's try again. Okay, we're good. Now, of course, if we run that, still nothing is going to happen because we haven't actually implemented anything yet. So I want to make some minor changes now into capp.h and capp.cpp. Let's look at those. capp.h first. Okay, so in capp.h, all we need to do is bring in these files. So under here where we hash include camera.hpp, we're going to add hash include /qb ray trace /qb textures /flat.hpp and hash include /qb ray trace /qb textures /chequered.hpp. Okay, save. That is everything we need there. Okay, so let's have a look how we can actually have a look at these. Let's look at capp.cpp. Right, so in capp.cpp, this is where we actually do the rendering. Now I've made some just minor changes here. So one thing I've done, under p window equals here, I declared two new variables. So int x size is 720 and int y size equals 720. We're going to do that. And then we're going to modify those so that we set the window size to those. Oh, no, I've done that wrong. My apologies. Don't go there, they go up here, of course. Above p window, that makes sense. And then, so here we set these to x size and y size, like so. You can probably see what we're doing here. This simply allows us to specify these. So we also then, when we initialize our image, yes, this becomes here is x size, comma y size, like that. Okay, so that just makes it easier to change our dimensions. Now, we have at the moment here, we have mscene.render, which is actually what renders our scene. What I'm going to do, I'm going to comment that out, okay? And in there, I'm going to put a new block of code here to set up a texture. Now, we're doing this here, not in the scene class, because, well, you'll see, okay? I think this is really worth doing. So qbrt, : texture. I'm going to try the checker first, so : checker test texture. Okay, so that will initialize an instance of that, and we're going to do test texture dot set transform. Okay, qb vector double of std vector double initialize with 0.0, 0.0, so that's our initial translation. Okay, we have our rotation 0.0, and we have our scale. Okay, qb vector double std vector double 4.0, 4.0, just like that. Okay, that will set the transform, and now what we're going to do is we're going to render the texture. So this will allow us to preview our textures. Okay, so for int y equals 0, semicolon y less than y size, semicolon plus y. This is just a good way of really checking that everything that we've done works the way it should. X less than x size plus x, right? And we're going to compute u and v. Compute uv, so double u is equal to static cast to double of x divided by static cast to double of x size divided by 2.0 minus 1.0, and v is much the same. Static cast to double y divided by static cast to double y size divided by 2 minus 1. So that gives us u and v that vary between minus 1 and 1. We then get the color from the texture. Okay, so qb vector double pixel color equals test texture dot get color uv chords. I didn't define uv chords, that of course goes up here. qb vector double uv chords, which we initialize with std vector double u comma v, just like that, and then we pass that. So that shows really how the textures work, and then we're going to simply update this pixel of the image. Okay, so m_image.setPixel x comma y comma pixel color dot get element 0 pixel color.get element 1 and pixel color.get element 2, just like that. Save. Okay, so what that should do, we've modified capp.h and capp.cpp, so now when we run our code, instead of rendering our ray traced image, we should instead generate a test version of our texture. So let's save that, let's compile and run and see if it works. So let's run make. Okay. What have I done? qbrt : texture : checker test texture. Checker is private within this context. Ooh, okay. Checker.hpp line 15. Let's have a look. Checker.hpp line 15. Indeed it is, because I forgot to specify public. Okay. Yes, it's worth noting these are all private by default if you don't specifically say public, so let's save that. So if we compile and run again, we should hopefully now work. It's going to run make clean, make sure, force it to recompile everything. Okay, that's good. So if we run ./qbray now, yes, there we go. So now we see in our window an implementation of our checker texture, which means everything is working correctly. So one thing we can do is have a look at how we can transform that. If I go back to capp.cpp, we defined our transform here. Okay, so we define things like an angle and stuff like that. I just want to show what that does. If we do m_pi divided by 4, let's save that and let's run it. Back to here, rerun make ./qbray. See, we now have a rotated texture. So, and we can play around with the scale and the translation. You can try all of that, and it does indeed work. So we can see that is the effect of the transformations. So that's really it for the implementing textures. The next thing that we're going to look at is how we can actually then apply those to our object. So everything is working. We should be in place to do that. We just need to go into the scene class and make some changes so that we can actually see some textures working. Okay, so let's jump in and do that now. Okay, so really just to demonstrate this, we've come into scene.cpp. I'm not going to go through all the typing here. I'm just going to talk through this code. If you can look at this up on the GitHub repository if you want to. So I've made some changes to the scene class basically to implement textures. So just to talk through it, we have a camera set up as before. We've changed the position slightly and things. And then now this is the new bit. We actually define some textures. So we define a floor texture, a sphere texture, a cylinder texture, and a cone texture. And we simply do that the same way we've done for everything else, using std : make shared, qbrt : texture : checker, because they're all checkers. That's all we have at the moment. The flat texture is pretty boring, so we're just going to use the checker one. And then we just set the transforms and set the colors for each of those accordingly. And we do some slightly different things to vary the scales a little bit. For example, for the cylinder, you have to take into account of the fact that the distance around the cylinder is the circumference, whereas the distance up and down is the height between -1 and 1. Okay, so there's a little bit of variation needed there. The code to actually create the materials is the same, except that occasionally we have a material where I've assigned a texture. So this is what we do. We create the textures, we create the materials, and then at some point we have our material and we use the assign texture function to assign to it, in this case the cone texture and the sphere texture, cylinder texture and floor texture and so on. Okay, and then we set up our object. So we have cone, left sphere, right sphere, floor, left wall and so on, and we simply set those up, we set the transforms, and then we call the assign material function to assign the material to that object. Because the material handles everything to do with the texture, that is really everything that we need to do. Okay, so we set up all of those objects, we push them back into our scene, and then we just set up the lights. So we've got here, I've put some lights at the back here just to illuminate brighten up the shadows a little bit. We're not doing global illumination yet or anything like that. We may come to that later. And then the rest of this code is exactly as it was before, that actually performs the rendering. So nothing much to see there really. So let's just save that. And we're going to compile and run, and let's have a look at the result that we get. Okay, so back to my terminal window. I just want to run make clean, just compile everything through from scratch. I guess if you were dealing with really large projects, you would never really want to do that. But even for the relatively large number of files we have here now, it's not really a big deal. So let's just run qbray. Okay. And for this scene, it is pretty slow. As you can see, we are probably developing the world's slowest ray tracer. But I'm not too concerned about that. I mean, really, what I want to create here is a platform that serves the purpose for education, for teaching and for learning how ray tracing works and all of that. We're not overly concerned with performance. There is quite a lot of optimization that we could do to the code that we have, and ultimately we could create it to run in a multi-threaded environment. So I mean, that's the logical way to really get speed with ray tracing, right? Is because every ray that you cast from the camera can be regarded as being independent. They don't depend on each other in any way. So you can really divide your image up into separate spaces, and you can then run those on different threads. I have a 6-core, 12-thread CPU here, so in principle I could make this go a lot faster. We may come to that later, but for now I think really, as I say, the performance isn't really an issue. And there we go. So that's with the code that we've written today. We now create the image that I had there for the trailer and everything else for this video. Now, you can see what I mean about the cylinders. There is a bit of a limitation with the way the texture changes between the surface of the cylinder itself and the end cap, and that may be something I come to look at again later. But for now, really, for what I want to do, this is really good enough. Okay, and I think that's really starting to get to the point that we can make some quite interesting images now. So there we go. That's really everything that I wanted to talk about today. We've covered the basic theory of UV space and texture mapping, how that works, how we can unwrap an object essentially to create a two-dimensional UV space representing that object surface, and then how we can go about calculating the UV coordinates from the point of intersection in Cartesian coordinates for the objects that we've defined so far, being planes, cylinders, cones, and spheres. Obviously, if we had any different types of shapes, we would need to consider again how we do that. For each specific shape, and that's fine for the geometric primitives. For more complicated shapes, there are other sort of ways that we can think about doing that, but that's sort of beyond what we really want to talk about now. And I think we're really getting to the point that it's possible to create some quite interesting images now. Okay, so as I say, that's really everything that I wanted to talk about today. This video has become quite a lot longer than I expected, as actually they always do. I should really expect that now, shouldn't I suppose? But there we go. So, as I say, I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have enjoyed it, please hit that like button. It really does help with the YouTube algorithm. And if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. I'm planning the next episode to start looking at refractive materials like glass and water, so that should be really interesting. Keep an eye out for that. Anyway, listen, it's been a pleasure. Thank you very much for watching, and I look forward to seeing you in the next video. Bye.